On a clear, windy night, a city glows. A familiar and reassuring glow against the dark landscape. This constant stream of electricity powers homes, businesses, infrastructure. The system that delivers this power operates largely unseen, a complex choreography of generation and delivery. We flip a switch, and the light comes on. This simple action is the endpoint of a vast network designed for one primary purpose: unwavering reliability. The entire apparatus is built to ensure that when you demand power, it is there, instantaneously and without interruption, day or night. Yet just beyond the city's edge, a different scene unfolds under the same windy sky. Rows of massive wind turbines, engineered to capture the very energy of the moving air, stand perfectly still. Their colossal blades, designed to spin and generate clean electricity, are motionless. This presents a puzzling contradiction. On one hand, a city consumes vast amounts of power. On the other, a nearby source of power generation, seemingly with ample fuel in the form of wind, remains idle. It is a disconnect between available resources and active production, a situation that appears to defy basic logic. Why would a system designed for continuous operation deliberately halt a part of its own machinery? This scenario is not a malfunction or an isolated accident. Instead, it is a deliberate action, a calculated decision made by the unseen operators of the electrical grid. The stillness of the turbines is a consequence of the same intricate system that keeps the city's lights on. This apparent paradox lies at the very heart of how our power grids function. The challenge is not simply about generating as much electricity as possible. It is about maintaining a precise, continuous, and delicate equilibrium between the amount of power being produced and the amount being consumed at every single moment. This balancing act is the most critical function of the grid. How can a system be simultaneously characterized by constant delivery and intentional restraint? What are the hidden rules that govern when a power source is used and when it is sidelined? The answer reveals that the stability of our electrical world depends on a complex interplay of physics, economics, and engineering. The sight of still turbines next to a lit city is not a sign of failure, but rather a window into the profound and constant struggle to maintain one of modern civilization's most vital systems. It forces us to look beyond the simple act of flipping a switch and question the deeper mechanics that ensure our lights stay on, until, for reasons we rarely understand, they don't. The electrical grid is a vast, interconnected machine, arguably the largest and most complex ever built. At its core, it is a network designed to perform a single, continuous task, moving electrical energy from where it is created to where it is used. This process begins at power plants, known as generators. These facilities convert various forms of primary energy: chemical energy in natural gas, kinetic energy of wind, kinetic energy of water, nuclear energy from uranium, into electricity. These generators can be massive, centralized power stations that serve entire regions, or smaller distributed sources like rooftop solar panels. Their collective purpose is to supply the raw power that energizes our world. Once generated, electricity cannot be stored easily in large quantities, so it must be transported immediately. This is the role of the transmission system. High-voltage transmission lines, the steel towers and thick cables that stretch across the landscape, act as the superhighways of the grid. By increasing the voltage to extremely high levels, operators can send large amounts of power long distances with minimal loss. This network links distant power plants to major population centers, creating a resilient web. That lets a city draw power from a hydroelectric dam hundreds of miles away. As electricity approaches its final destination, it enters the distribution system. This is the part of the grid we see every day: wooden poles, smaller neighborhood wires, and local transformers. Here, High-voltage electricity is stepped down to lower, safer voltages suitable for use in homes, offices, and factories. The distribution network branches like a tree, delivering power down to individual service connections. It's the final, crucial link, the last-mile delivery to outlets and appliances. Every light, computer, and machine is a final node in this sprawling network. The final participant is the consumer. Every individual, household, and business that uses electricity is an active part of the grid. The grid doesn't push a fixed amount of power to users. Instead, consumers draw power based on immediate needs. Turning on a television, starting an industrial motor, charging an electric vehicle. Each action is a real-time demand on the grid. The cumulative effect of millions of actions creates a constantly shifting total load, which the rest of the system, generators, transmission lines, distribution networks, must react to and satisfy in perfect synchrony, second by second, without fail. Overseeing this network is the grid operator, the impartial conductor of an electrical orchestra. They don't own the power plants. Instead, they direct the flow of electricity using sophisticated energy markets. Generators offer to sell power, and the operator creates a dispatch schedule, selecting the lowest cost combination to meet forecasted demand. But forecasts are never perfect. To handle unexpected events, the operator constantly makes real-time adjustments, maintaining the delicate balance required for a stable grid. The most critical balancing act performed by the grid operator is maintaining the system's frequency. In North America, the electrical grid is designed to operate at a precise frequency of 60 Hz. That means the alternating current changes direction 60 times every second. This frequency is a direct indicator of the real-time balance between supply and demand. If generation exactly matches consumption, the frequency stays at 60 Hz. If consumers use more power than is being generated, frequency falls. If generation exceeds demand, frequency rises. Target frequency 60 Hz, generation sours demand, and demand generation lines. Stability is paramount for the grid's health. Even small deviations from the target frequency can cause major problems. Many devices, especially those with electric motors, are designed to run at a specific frequency. If frequency strays, equipment can be damaged, and instability can spread. A sustained drop in frequency signals overload and risk of cascading failure, potentially a large-scale blackout. To prevent that, the operator must balance not just hourly averages, but moment to moment. That requires constant monitoring and instantaneous adjustments to power plant output across the interconnected system. Operators maintain several types of reserves to prepare for the unexpected. Reserves are plants available on short notice but not currently dispatched. Spinning reserves come from generators already online and synchronized, running below full capacity. They can ramp up almost instantly. Other reserves are offline plants that can start and connect within minutes to cover big shortfalls. Generators, operators, markets, reserves. The system is designed for near-perfect equilibrium. Supply must follow demand precisely. Frequency and balancing are physical laws governing grid stability. The constant effort to maintain balance is the central drama of grid operations. Every decision, which plant to run, how much reserve to hold, the price of electricity at a moment, all serve one goal: keeping the system balanced and the lights on for everyone. They generate powerful system-wide effects. The most immediate is economic volatility. When the grid is stressed and supply-demand balance becomes precarious, wholesale prices can swing wildly. In scarcity-reflecting markets, a small shortfall can cause prices to leap from a few cents per kilowatt-hour to several dollars per kilowatt-hour. These short-lived price spikes create enormous financial risks for utilities, for large consumers who buy in that volatile market. Costs ripple outward, hitting households and businesses. Utilities must manage this financial risk. They may pass costs to consumers via fuel adjustment charges on bills, or they may buy complex hedging products to lock prices, but that insurance cost is embedded in rates. Hidden fragility becomes a tangible economic burden, making energy less affordable. Maintaining reliability requires more investment in ancillary services. Grid operators procure more reserve generation to stand by. Reserves respond to faster frequency deviations of a low-inertia grid. Reserves also cover forecasting errors for renewable output. These services are essential for stability, but represent significant operational cost. Power plants must be paid to stay available, even without producing energy. This is a direct reliability tax on the system. The consequences shape behavior across the economy. Extreme price volatility can deter industrial investment. Factories with high energy needs hesitate to locate in unstable regions. The debate intensifies. Should all consumers pay through higher rates? Or should costs be targeted at specific users or generators? Grid instability reshapes financial risk, consumer costs, and investment decisions. We began with a city's lights burning bright while nearby wind turbines stood motionless. This isn't a paradox, but a logical outcome of the system's design. The stability of our power supply is forged in the slow-moving interactions between market rules, physical laws, and infrastructure. The physics, economics, and operational realities have evolved at different speeds, creating a brittle system. This raises a critical question. In a low-carbon grid, who should pay for reliability? Should the cost be socialized across all consumers, treating stability as a public good? Or should it fall on renewable energy owners, potentially slowing the green transition? There is no easy answer. Our future power supply depends on how we choose to resolve this fundamental tension. You've been watching System Atlas, exploring how the world's systems really work. Share your comments below. See you in our next episode.